Hi all, let's continue with the sign magnitude division. So today we are going to discuss about the flowchart of sign magnitude division operation. So this is a flowchart of sign magnitude division operation. So in the division operation we have a dividend and a divisor, and as a result we will get a quotient and a remainder. So the division operation, it takes a dividend and divisor as an input. So the dividend, it is stored in A and Q registers. As we have 2n. The length of your if the length of your divisor is n bits, the length of your dividend will be 2n. So the dividend requires two registers A and Q to store your dividend, whereas your divisor is stored in a B register. And the sign bits of your dividend is stored in AS and QS, and the sign bit of divisor is stored in BS respectively. So after the division operation is performed, the quotient will be stored in Q register and the remainder will be stored in A register. From this left hand side, where you are going to, this particular left hand algorithm is going to check whether you have a divide overflow situation or not. And if you have a divide overflow situation, you cannot continue with performing a division operation on the magnitude part. So we'll first check if there is a possibility of a divide overflow. If there is a possibility of if there is an overflow situation, then we are going to the hardware is going to set the DVS flip flop to 1. DVF, divide overflow flip flop, is set to 1, and we stop the process. We don't move with the continue with the division of magnitude parts. So first we will check with divide overflow condition. So as I already told you, a divide overflow situation occurs if the dividend bits, which are the most significant bits of the dividend, which are stored in the register A, is greater than or equal to the divisor B, then we say that a divide overflow situation occurred. So based on that situation, the divide overflow flip flop is set to 1 by the hardware or by the software. So for that, in order to find out that, in the flowchart, you are first going to calculate the sign bit of your quotient. So when you perform a division operation, you obviously get a quotient. So you have to first see what should be the quotient sign of your quotient. So that is, you can get that from the sign bit of your dividend and the divisor. So you are going to perform an XOR operation. If both the dividend and divisor are signs are equal, then you get a positive sign for your quotient. So if both the dividend or divisor are either both are positive or both are negative, then the quotient will be positive. If any of the dividend or divisor contains a negative value, a negative sign, then the quotient will also get a negative sign. So based on that, we are performing an XOR operation on the signs of AS and DS. Next, sequence counter is set to n minus 1. So n minus 1 is represents the number of bits of your divisor. So this value represents the number of bits of your quotient also. So the number of bits of your divisor is same as the same number of bits you will get for your quotient. So it is set to n minus 1. Next, we are performing a subtraction operation on the contents of A and B. So A contains the half of your dividend, the most significant 5 bits of your dividend. You are performing A minus divisor. So A minus B can be represented as A plus B complement plus 1. So that result will be stored in E and A register, E flip flop and A register. So based on the carry bit which is stored in E, we are going to determine if A is greater than or equal to B or A is less than or equal to B. So if A is greater than or equal to B, based on the overflow condition, we say that there is an overflow, which means the quotient that you get out of this division, which it requires more than 5 bits, more than the capacity of your quotient register. Then we set the divide overflow flip flop to 1. So after performing this subtraction, if E contains a value 1, we mean to say that a divide overflow has occurred. The hardware or the software will determine that a divide, there is a chance that divide overflow occurs, and it will set the divide overflow flip flop to 1. Now we have performed the subtraction operation here just to check if there is a divide overflow. So now we have to get back the original result of A. So for that we are again performing an addition operation. Say the content of A register is 15. I'm performing and B is 8. So to check this value, E value, I'm performing A minus B, 15 minus 8, right? When so this is just to check whether the divide overflow occurred or not. Now I have to get back my A value. So what I have to do, I have to again add 8 back to the result to get the original value of A, right? So that is done in this particular step. Okay. So I'm performing A plus B to retrieve the original value of A and setting the divide overflow to 1. So when there is a divide overflow, you cannot move with the division, continue with the division operation. So I'm going to end this. So if E value is equal to 0, it means that A is less than B. So in that case, here also I have to reinstantiate the value of A. So for that I am performing A plus B back to get the original value of A and E. And I am setting the divide overflow flip-flop to 0. Whenever this divide overflow flip-flop is set to 0, it will continue with the division operation on the magnitude part of your data. So in the divide magnitude parts, I'm going to first perform a shift left operation on the contents of E, A and Q registers. Okay. After performing a shift left operation, so what happens in the shift left operation? The qnth bit, at the qnth bit, you are going to insert a 0, and from there it moves towards the left. All the contents of the registers E, A and Q will be moved towards your left. Now, after performing a shift left, I am going to check the value of E. If E is equals to 1, we know that EA is greater than B. Okay. In that case, we have to subtract B from A and you have to insert 1 in the qnth bit because A is greater than B. Okay. So, if E is equal to 0, you have to subtract A minus B, okay, and again you have to check the value of E. So when your value of E is equals to 1, then you have to insert 1 into qnth position. If the value of E is equal to 0, it means that A is less than B. In that case, you have to perform an addition operation on the contents of A and B and decrement your sequence counter. At this side, when E is equal to 1, you have to add A minus B, perform a subtraction of A minus B, and the resultant value will be the value of A. And it means that it is A is greater than B. So you have to insert 1 in the qnth position. And sequence counter should be decremented by 1. And now you have to check the sequence counter. If the sequence counter is equal to 0, we'll stop the process, and whatever is there in Q, that will be your quotient, and whatever is in A, that will be your remainder. If sequence counter is not equal to 0, we'll again continue with the same process from the magnitude, dividing the magnitudes until your sequence counter reaches 0. The first step before performing a division, we have to check if there is a divide overflow condition. If there is a divide overflow, then this devious flip-flop will be set to 1 and we stop the process. If devious flip-flop is set to 0, which means there is no possibility of a overflow situation in this division algorithm, then we continue with the dividing the magnitude part of your data. Initially, the dividend is in AQ and the divisor is in B, and the sign bits are in AS, QS and BS respectively. After the division operation is performed, the quotient is stored in Q and its sign will be stored in QS, and the remainder will be stored in A, right? So the sign of the result at the left side, first we are going to find out the sign of your result is transferred into QS by using AS XOR BS. So next we are going to set the sequence counter which specifies the number of bits of your quotient. Next you are going to check the divide overflow condition. So this is done by subtracting the divisor which is present in B from the half of the bits of the dividend which are being stored in A. So if A is greater than or equal to B, It means that there is an overflow situation in the division. So we are going to set DVS flip-flop to 1 and we are going to terminate. If A is less than B, it means that there is no overflow condition. In this case, we are going to set DVS flip-flop to 0 and the value of dividend, both the cases, the value of dividend is reinstated by adding B back to A. So that will give you the original value of A. So this is in case of for checking the divide overflow situation on the left side of your flow chart. So next, if your divide overflow is 0, we'll start with dividing the magnitude parts of your data. So the division of magnitude starts with the dividend in AQ and in the left of the, so your dividend will be stored in A and Q registers and you have your E flip-flop. So you are performing a shift left operation on the contents of E, A and Q. After performing a shift left, we are going to check the value of E. If E is equal to 1, then we must subtract B from A and then you have to insert 1 in the qnth position. Okay. In the shift left operation, if E contains 0, then the divisor is subtracted by adding its 2's complement value. If E is equal to 0, then you need to subtract A minus B and EA contains the result of your A minus B, where E contains your carry bit. Now, based on E, if E contains 1, it means A is greater than B. So, you are going to set the qnth bit to 1. If E contains 0, it means A is less than B. So, you are going to, and the original value is reimposed by adding B back to A. So, you are going to here reimpose the original value by adding A back to B here and decrement your sequence counter and then check your sequence counter. So this process is repeated until the register A repeated with the register A containing the partial remainder. Whatever is stored in A, that will be the partial remainder which is given as an input back. So this is how you continue this process until the sequence counter is equals to 0. So this is about a sign magnitude division algorithm. Thank you.